All right, next up we're going to try one more. This time I'd like to evaluate the triple integral over the solid E of y squared z squared dv, where E is going to be bounded by the paraboloid x is equal to 1 minus y squared minus z squared, and x equals 0. Now this one's going to be a little bit more difficult to visualize drawing it in 3 dimensions. So what I'm going to do is try drawing it in 2 dimensions, and we'll go over the traces associated with this. So let's start off with the xy trace. And for the xy trace, we're going to neglect the z that's here. Think of this as setting z equal to 0, and we'll take a look at what we got. So here's our x-axis, our y-axis. So disregarding the z, we would have x is equal to 1 minus y squared. That would be a parabola opening to the left, like so. And x equals 0 would simply be the y-axis. So the region in question would look like this. If we were to consider the xz trace, we disregard the y that we have here, and we consider what's going on in the x and z direction. Well, this would be x is equal to 1 minus z squared, and we would have essentially the exact same picture as what we had to our left. So x equals 0 would be the z-axis, and x equals 1 minus z squared would be a leftward opening parabola. Now, if I take just these into consideration, then it looks an awful lot like a, well, it's a paraboloid that's opening toward the negative side of the x-axis. However, if we were to consider the yz trace, I would be taking this x equals 0 and plugging it in over here. Solving would give me y squared plus z squared is equal to 1, meaning that the cross-section in the yz plane is going to be a circle of radius 1. Now, I'm going to do my best here, but we'll see how this actually goes. I'm going to try drawing this in 3 dimensions so that we can get a little bit better visualization as far as what's going on. So here's our x-axis, our y-axis, and our z-axis. What I'm going to do is try to draw this circle first. So going up 1 unit on the z-axis, 1 unit down the y-axis, 1 unit down the z-axis, and 1 unit down the negative y-axis, we would have a circle passing through these 4 points. And again, trying my best. Good. We can then go 1 unit down the x-axis and put a vertex of the parabola there. And have this paraboloid open this away and this away, but then also this away and this away. So definitely not the best picture I've ever drawn, but hopefully the xy trace would be this parabola right here. The xz trace would be this parabola right here, and the yz trace would be this circle coming around. So this solid here represents our solid E. Now, taking a look at these, the first decision that we get to make is we would like to integrate with respect to what variable. Now, all things considered here, when I take a look at this with x as a function of y and z, and x equals 0, I am definitely thinking to myself, I would like to integrate with respect to x first. So the order of my integration, for now, I'm just going to call it dx dA. So first we'll be integrating with respect to x. Now these would be our 2 bounds that we have on x. So this will extend all the way up to the paraboloid and extend all the way down to x equals 0. I guess from this perspective, based on these 2 pictures right here, what we're saying is that the paraboloid is on the right and x equals 0 is on the left. Now with that in mind, when I take a look at the yz trace of this, our double integral is supposed to take place over this region. I wouldn't want to consider this as type 1 nor type 2. What I would want to do is convert this into a polar region. So what I'll do after this is convert y and z to polar. So with that in mind, I'm going to use y equals r times the cosine of theta and z equals r times the sine of theta. Please know that this is completely arbitrary, and if you wanted to reverse this order, it would be okay. That way, dA can be interpreted as r dr d theta. That's the dA that gets left over here. And additionally, we also get that y squared plus z squared is equal to r squared. Now, one of the reasons that that is significant for us is due to the fact that the equation of our paraboloid, x equals 1 minus y squared minus z squared, can now be interpreted as 1 minus the quantity y squared plus z squared, telling us that the paraboloid can now be bounded by 1 minus r squared. So that is going to change our upper bound on x into simply 1 minus r squared. So I want to bear all of these things in mind as I set up what our triple integral is going to look like. So I'm going to recopy this triple integral on our next page. It'll be triple integral over the solid E of y squared z squared dv. Now, the other thing that I'll need to do is actually interpret the yz trace of what we have going on here. This is y squared plus z squared is equal to 1. We can interpret this as r going from 0 to 1 and theta going from 0 to 2 pi, one full trip around the unit circle. So when I set up my triple integral, those will be the bounds that I'm using on r and theta. I think now we're ready to make the trip. So let's see what we can get done. This is going to be equal to, last integral will be with respect to theta. We said that'll be 0 to 2 pi. Second integral will be with respect to r, that'll be 0 to 1. And the first integral is going to be with respect to x. That is going to go from 0 to the newly converted 1 minus r squared. Y squared will become r cosine of theta, quantity squared. And z squared will become r sine theta, quantity squared. dv will become dx dA, and dA will become r dr d theta. Now the good news here is we have no x's in here. So when we integrate with respect to x, that'll simply be all of these constants times x. So I'm actually going to do two steps here. The two steps that I'm going to do are simplify algebraically what we have going on here with all of the r's. So this will be r to the fifth times sine squared theta times cosine squared theta. And I'm going to integrate that with respect to x. We'll get x. This is going to go from lower bound 0 to upper bound 1 minus r squared. And we'll retain our dr and d theta. Next up is to actually plug in those bounds. And we will get r to the fifth sine squared theta times cosine squared theta times 1 minus r squared. Plugging in the lower bound of 0, we'll simply zero everything out. At this point, we have ourselves down to a double integral in polar coordinates. I would like to point out that this can be factored into a function of r times a function of theta, and our limits, our bounds, are all constants, which means that we can use Fubini's shortcut. Applying Fubini's shortcut, we will get a definite integral from 0 to 2 pi of the sine squared of theta times the cosine squared of theta, d theta. And for r, we'll have the definite integral from 0 to 1 of r to the fifth times 1 minus r squared dr. Now, both of these are going to need some alterations in order for us to actually evaluate them. The algebra for the r is going to be a little more straightforward, but over here, this is going to be a little less straightforward. There is a power-reducing identity that can be used anytime you have equal powers of the sine and the cosine. That's making use of the double angle identity for the sine. The sine of 2 theta is equal to 2 times the sine theta times the cosine of theta, which means that the sine of theta times the cosine of theta is equal to the sine of 2 theta divided by 2. Squaring that will give us what we need here. So this will still be the definite integral from 0 to 2 pi. When I square this, I am going to get 1/4 times the sine squared of 2 theta. That looks terrible. I will fix that in the next step. Over here, distributing the r to the 5th power will give us r to the 5th power minus r to the 7th power, dr. That's ready for some power rule. This one's actually ready for another power reducing identity. Definite integral from 0 to 2 pi. We'll take the 1/4, leave it out front, and apply the power reducing identity to our sine squared. Power reducing identity for sine squared is 1/2 times 1 minus the cosine of, well, double the angle, so double the 2 theta. Man, I just can't get this theta integral to look nice. Quite frankly, I blame the government. Not because it's their fault, just because, you know, I can. All right, so let's see if we can evaluate these definite integrals. We'll take the 1/4 and the 1/2, pull them outside of the integral as constant multiples. That'll give us 1/8. Then evaluating these two integrals will give me theta minus sine of 4 theta divided by 4. That's going to go from 0 to 2 pi. And this other one, applying the power rule a couple times, this will be 1/6 r to the 6th power minus 1/8 r to the 8th power, going from 0 to 1. Now, good news is, plugging in 2 pi or plugging in 0 for theta, in both cases, the sine of 4 times that angle is going to be 0. So the only non-zero term that we get from the first part is going to be 2 pi. From the second set of brackets, plug in r equals 1, we get just the coefficients. Plug in 0, we get a lot of 0. Taking 1/8 of 2 pi is going to give us pi over 4. And 1/6 minus 1/8 will be 8 minus 6 all over 48. That's 2/48. That reduces down to 1/24. Final answer for this one is going to be a nice solid pi over 96. Now, we didn't have to integrate with respect to x first. We could have left this in Cartesian coordinates instead of making a conversion to polar, but trust me, try the problem for yourself, and you will want to do it this way as well. Thumbs up.